Chapter 16 is just the beginning. Actually, probably a good third of this course is devoted to the study of electricity and the flow of electricity and its relationship to magnetism, which is really cool. And I'm trying to work on one of our meetings will be around magnetism, but we'll see how we do, how we get there. This is a really important unit, and the reason I feel that way is because this is a central element to everything we're doing. So you use electricity so much, and the essential question for humanity in the 21st century is around energy, and energy in all its forms. So how do we make enough energy and not kill the environment? And how do we share energy in ways that are equitable around the world? And how do we make sure that folks who are on the fringes can improve their opportunities by giving them electrical connections and also an internet too. So one of the things that happens is that we hide electricity from people a lot out of the concern, out of the, what's the term, abundance of concern. So that all the stuff that carries electricity around is actually in the walls, and it's hidden from you. So we're going to try and uncover that a little bit. I actually had a lot of fun last weekend because I was doing some electrical wiring in my house, and I rerouted a bunch of things, and it was really satisfying. In Vermont, you can do that. You don't have to necessarily hire an electrician as long as you're willing to take accountability for blowing yourself up. But that didn't happen, thankfully. And I'm not going to teach you how to do wiring in your house, but you should have a good awareness about what's going on, and you should be aware of safety. So we're going to go down through, and we're going to get to this bullet here, problem solving with Coulomb's law. And then when I see you next, it's going to be about electric fields. So we'll hop over the next slide and then come to this absolutely ridiculous diagram. So everybody will know that we're trying to talk about an atom when you see a diagram like this, but it's absolutely absurd. It doesn't have any connection to modern theory. And the first problem I have with it is that, yes, of course, the nucleus is very dense, and that's where all the positive charge is, which should get you thinking about this. Positive charges repel each other. So why do they stay there? That's kind of weird. And then, of course, in the diagram, we have equal numbers of negative charges to make this a neutral atom. But if I was a neutron, my electrons would be, I'm here in Essex, my electrons might be in Brattleboro or, St. Johnsbury or Montreal. So this scale is totally whacked. Because in actuality, if you compare the diameter of the nucleus to the diameter of the electron cloud, then that's about 5 orders of magnitude different, which is not going to fit on this slide. And the other issue too is that they're depicted as particles in sort of a planetary orbit, and we know that's not true either, that the orbits are not circular, and actually the orbits are more based on probability of where the electron is likely to be. And the electron even has wave-like properties. So yeah, not this. But for starters, what we really mean, that the reason why we use this diagram is to show that the positive charges are held in the nucleus with very, very strong forces, and they are not coming out. So when we quote charge something, we're moving electrons. So sometimes we can trap electrons on something, and if it has excess electrons, it's negatively charged. And if it's electron deficient, that means somehow we've stripped electrons away from it. So it's all about balance. And when something's charged, that means that there's an imbalance. But it's all about the electrons. That's the big takeaway. And so, when I slow down like this and really talk about a slide for a while, that usually means there's going to be a conceptual question based on this. And the conceptual question here would be, what does it mean to be charged? And that's with electricity, not in a legal situation, just to clarify. Right. Another interesting way to think about it is um, this famous molecule, the good old H2O. And not only does it do interesting things in terms of bonding, but it's polarized, and you can actually do a lot of electrostatic work with water. It's actually pretty good at it. So conductors and insulators, it's pretty straightforward. Um, Metals are good conductors, just like they're good conductors of heat, and it's because they have valence electrons that are not held very tightly. So they're really good at having energy sharing collisions, and they're also really good. They're really easy to move from point A to point B with just a little bit of influence. So what does it mean to be charged? Well, I'm just going to pause for a second, and this is where I want to go off and take a look at that video that I had pulled up. And let's see where that is. It's right underneath my menu. I think it says, yeah, here it is. All right, so I'm just going to play this. Thumbs up if you can see the video, just so I know. Yay. Thank you. And let's see if I can, yeah, okay, we're good. Right, so as we're watching this video, with obviously security camera footage from a gas station. Whoops. – 2004. So this is 16 years ago. And this young woman's 30 seconds of fame. So when she gets in the car, she actually makes a mistake. And there are warning signs on the gas pump. It would be a good idea to read them again. Make sure that doesn't happen. Yikes. So we were just talking about what it means to be charged. And I'm just going to play this one more time, and we'll pause it just to consider what her mistake actually was. And you can think about it too. So again, young lady pulls up to a gas pump, gets out. The clothes she's wearing is probably a contributing factor, and the cloth seat, I'm pretty sure she did not have leather seats in this vehicle. All right, so she goes to start pumping the gas. Now again, I'll just mention, if you haven't read those warning signs at the gas pump in a while, you might want to do a refresher course, because using gasoline is a huge responsibility. It's extremely volatile, meaning that vaporization happens really easily with gasoline. We have a lot of safety features on the gas pumps to try and prevent this vaporization from happening. But it still does. So she is seated in her car. Let's just check this out for a second. So her feet are off the ground. She's sitting on the car seat. And let's see how she exits. Okay. As she exits, she doesn't touch anything. So she kind of slides out of the seat and then walks to the pump. Now, if you've ever been shocked when you went to close a car door, then you can actually relate to this. Because if you have cloth seats and you have, you're wearing some cotton or polyester, and you kind of slide out of the seat, that rubbing motion has actually caused you to be charged. And we don't know if it's having extra electrons or being electron deficient, but we know there's an imbalance. And there's an imbalance between you and the car. So if there's any contact with a conducting surface, then there's going to be an attempt of the charges to neutralize that imbalance. When she was sitting in the car, everything was an insulator, and she slid out of the car and she didn't touch the car door or anything like that. And so she actually acquired a significant static charge. And when we let this play, right before she touches it, you can see she's going to reach out and touch the gas pump and probably had a little spark. Now what's burning is the gas vapor that's around. It goes up really easily. So, words to the wise, don't ever try to start a fire with gasoline, and make sure your friends don't ever try and start a fire with gasoline, because it's playing with fire. If you're trying to get like a little campfire going, you pour some gasoline on it, and then you walk away to go get matches. While you're walking away, these gasoline vapors will start building up into a small cloud. And it's almost always much bigger than people expect. So when they strike a match, it ignites the cloud. They're thinking they're going to strike a match and toss it into the gasoline that's in the campfire. And no, actually, strike a match, it's going to ignite the cloud that you're standing in. So very dangerous. And in the aftermath, so the cloud just burns up really quickly, and then it settles down. And then she decides that she's going to pull that out. I don't know if you noticed it, but I probably would have, done that also, because the fire went out almost immediately. And then if you continue to have like lots of flames around here, it's going to kind of mess up your car a little bit, your paint job. Right, so how can you prevent this? One more time. So when she gets out of the car, right here, here's a really good habit to get into. When she gets out of the car, if you don't like being shocked by a car when you get out of it, then grab onto the metal door frame as you get out. You can put your hand here on the front of the door or on top or whatever it works. But if you have a hand on the door is made out of metal, it's a conductor. And so as you slide out of your car, it's not going to let an imbalance build up, because the excess charge is going to reroute itself through the car door. So that's the key. Hold on to a metal part of the car door and you'll never get shocked again. Or if you're like me and I love getting shocked, then this gives you a clue about how you can amplify the effect. Really squiggle around in that seat. And then when you get out, make sure you only touch insulating materials. And then when you're ready, then you can touch the car door. And it usually goes snap. And it's highly invigorating. Okay. Good. So hopefully, that's just the sort of the tip of the iceberg about why it's important to pay attention to this electricity stuff. All right, I'm going to go back in there. Keep on plugging away. This poor lady, this has been viewed like 700,000 times. And you're probably going to show your friends too. So. All right. Get me out of here. There we go. Let's see where we left off. Well, we were talking about charging things. So this is charging by conduction. The key idea is that we have two pieces of metal, and we bring in one piece of metal that's, quote, charged, it's electron deficient. And when we put it in contact with the other metal rod, well, metals, like we said before, they have a lot of conduction electrons that are valence electrons that are not held very tightly. And so it's really easy for them to move around. And when they see an object that's electron deficient and they're floating around here, they're like, we can fill a few vacancies. So they hop over. And when they hop over, they leave vacancies behind, and then they neutralize some vacancies on the other object. So when we touch two things together, they both wind up sharing the same charge. And that's charging by conduction. So the key idea is that conduction, or charging by contact, winds up transferring the same charge to the other material, so that the two roughly have about half of what the original was. Here's a clever alternative to that, and it uses the concept of ground. So Monday night, we were taking a look at the concept of ground. It's an infinite supply, whatever you need to balance out a situation. And so in this case, we have a conductor that's connected to ground. Then we bring something that's negatively charged in. That means it's got a surplus of electrons. And that negative charge, notice they're not in contact. That negative charge is going to drive away electrons from this object. So if we hold it there while we disconnect the ground and then take this object away, then you'll see that it leaves behind a positive charge because some of the negative charges got stranded when the grounding wire was removed. Okay, good. Now, non-conductors can also be affected by the presence of charges nearby, but usually what happens is they experience polarization. So the molecules can sort of have a change in orientation so that they tend to line up with whatever positive charge is brought nearby. So let's take a look at this charging thing. I have a silly little simulation here. We can run that. The old balloon trick. So a lot of balloons are made out of latex. And latex is primarily polymers. And polymers are long chains of hydrocarbons that have little H's sticking out. So you probably remember that from chemistry. And the little H's that stick out, that those hydrogen atoms are experiencing a covalent bond with carbon somewhere. And so the hydrogen's one electron actually spends a lot of time hanging out with carbon, pretty tightly held. And so that means that these H's that are sticking out would be really happy to pick up an electron or two. So this material, because it's made out of hydrocarbons. Oh, that's a big dog. Sorry. So these hydrocarbons have hydrogen stems that are kind of sticking out, and they're super good at picking up spare electrons. So that's an easy way for this thing to get charged. Even though it's not a conductor, it's very easily charged. And so we move it over sweater, and you can see that we're scooping up negative charges. And going to catch them all. Yeah. So now the balloon has excess electrons, and the sweater is electron deficient. And they'll have a tendency to want to hold themselves together. But then if we bring it over to the wall, whoop, come on, stick to the wall, stick to the wall. There we go. So now it sticks, and you can see when I brought it over, it had a tendency to cause an orientational shift in the molecules in the wall and sort of rotating the molecules so that they tend to have a positive side pointing towards the balloon and a negative side pulling away. And so the reason why the balloon sticks to the wall, even though the wall is technically uncharged, that charge polarization has been induced, and that's why it sticks. All right, and now so that's our conceptual understanding. Now for the good stuff, the math, yay. The name of the game is Coulomb's Law, and you're going to see a lot of French, right? So the B is silent. There are a couple of French names in here. So Ampere, for example, is a French name. Coulomb is a French name. And what else? Well, we'll see. And Volts is actually an Italian name. So Alessandro Volta was a really crazy person, lived in the 18th century and he essentially did make the first battery, but he used it to try and bring dead things back to life. So his favorite parlor trick was to take frogs' legs and then zap them with a little current from his battery and make them jump. So he thought you could bring the dead back. Yeah, all these people, they had a dark side. Right. Um, so with Coulomb's law, and that's right here, we can see that it's really similar to the gravitational force. So Coulomb's law is an attraction or repulsion between two charges, and it depends on how strong the charges are, and it depends on how far away they are. It really depends on how far they are away because it's squared. So that's a big deal. And then as we take a close look, they're very similar. So gravity is a force of attraction between two masses, and it is inversely dependent on the distance between their centers squared. So this is the same thing. It depends on the two charges and the unit that we use to measure distance squared. Right? So over r squared. Then there's a k up front, that's a constant, and then g, this is the universal gravitational constant. So they definitely look very similar, but k is so much bigger than g. G is very, very small. And so it means gravity is a very weak force. So what is it then if an atom is mostly made up of empty space? Why is it when I slam my hand down on the table that it doesn't just go through the table? What's keeping my hand from just going right through if an atom is mostly empty space? And the shorter answer is it's all electrical forces holding the molecules together. So that's why. I mean, in physics 1, we kind of called it matter, but now in physics 2, we're a little more sophisticated. We're considering the very, very small. So yeah, matter doesn't really exist by itself. It's made up of atoms and molecules. But we knew that already. So gravity is super weak, K is very strong. All right, let's go. Yeah, and this is terrible too. I don't like this. The only reason I included this slide is to tell you how terrible this is. So what they're trying to do is talk about Newton's third law here. So for every force, an equal and opposite force is blah, 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 blah. So what they're trying to do is look at this with notation. So F12 is the force on 1 due to 2. F21 is the force on 2 due to 1. It's just a mess. So I have a different way of doing it. Shocker. There's lots of different ways of doing things. And let's start off here. Okay, I'm going to stop sharing and change my screen. Hello. I think we're just going to go straight through tonight because, taking a break, we're actually almost at the end of the new stuff. So if that's cool with you. All right. So changing my video so I can get up to the board. And this would be a good thing if you could have the agenda on a different tab or something like that, just so you can bounce around. Because if you miss any of the numbers that I'm talking about, then that's where you can find them. Okay. All right, my sweet document camera. I love it. Did I tell you I got this document camera in March for $200? And I liked it so much I wanted to get another one last week, and it was $500.
Step up.
Yeah. gouging. Yes, the socialist in me will say they're price gouging, and then the capitalist people will say, no, it's just supply and demand. All right. So let's see. So let's start off with number 4, pretty straightforward. We're going to calculate the repulsive force between two protons that are a very small distance apart. All right, here we go. Sorry, there's a dog that in the way. All right, great. Just trying to get you so you can see me a little bit. Maybe I should lift that screen up a little bit. Okay, we're in focus. Excellent. Okay, so we have two positive charges that are close proximity to each other. And the distance between their centers is 5 times 10 to the minus 15. Meters. So that's the distance between their centers. And each Q, well, it's a proton, right? So our abbreviation for a proton is usually P positive. There we go. Okay, great. And so the charge on the proton is very small. So it's 1.6 times 10 to the minus 19. This is the so-called elemental charge. And an electron is the same thing, except it's negative. So negative 1.6 times 10 to the minus 19 coulombs. So now we can apply Coulomb's law. So the force equals K times Q1 times Q2 over R squared. So the K value is a fixed number. K is equal to 9 times 10 to the 9th newtons meters squared over Coulomb squared. Let me get out of the way so you can see that. Make those decimal points nice and dark. All right, how's that coming across? Excellent. Yes, so this is a constant. And on my graphing calculator, I actually plug this in as a constant. So when I'm doing problems, I can just say, hey, I use the letter K to represent it. But speaking of calculating this, let's see how this is going to work. So as far as the whiteboard goes, I'll write it all out. So this is 9 times 10 to the 9. And then I have two of these, they're two protons. So I could actually just write this as 1.6 times 10 to the minus 19 squared over this number squared. Ten to the minus 15, and that squared. Great, curious to see how this comes out. So the numerator is definitely smaller than the denominator, but then we have this big old number here. And again, underlining the fact that the electric force is very strong. That's what holds everything together around us. So thankfully, it's very strong. And also, thankfully, gravity is really weak because any two masses attract each other. And that means that the cars out in the driveway, you know, if the gravity was stronger, they'd be trying to exert forces to come together. All right, let's talk about how to calculate this. So if I write this in scientific notation, it reminds me about how I want to type this into my calculator. So a lot of calculators use this E, capital E, not the lowercase e that's used with natural logs, but to represent scientific notation. And then we'll multiply that by 1.6 E minus 19 squared. So if you write in scientific notation, you don't have to use parentheses. And then divided by 5E minus 15 squared. Okay, go ahead and give that a shot, and let's see what you get. Why don't you type in the chat once you get a number? We'll just compare things and see how you do. Let's sit down and pull up the chat. All right, let's see what you get. Winner, winner, chicken dinner. Yep, 9.2 newtons. Looks good.
I did not get 2 newtons.
Yeah, so I like starting off with this because, so that's newtons. So let's just kind of finish off what we're talking about. And remember, I was making the point together that the positive charges do repel each other in the nucleus. There's no question about it. And it's not a small force either, because 9.2 newtons is going to be approximately equal to 2 pounds. So that's crazy that there's 2 pounds of force trying to blow these protons apart, right? So this would be a situation that's happening in the helium nucleus where you just have 2 protons. And there's a lot of force trying to push them apart. So that's, again, making our point that whatever force is holding the charges, positive charges in the nucleus must be really, really strong. And so those protons are not coming out. So whatever we do to charge or make electricity move is only going to be electrons. Now, if you didn't get this number, it's definitely syntax. Right? So maybe you want to try to use some parentheses or something.
So I actually did it with parentheses to start, and then I did it without the parentheses, and I got it right. So I think it was just to calculate. I put it in wrong.
Yeah, yep. All right, that sounds good. So let's head off and take a look at the next one. And it says a person scuffing their feet on a wool rug accumulates a net charge of 42, and then there's a funny unit. So let's do that. So it says negative 42, and what is this thing? We're actually going to see this quite a bit. So C is standing for coulombs. That makes sense. And this Greek letter mu, this is a, if you're going on a parade and you want to carry a U around, and you put a little post on it. And it stands for 10 to the minus 6. So this is really negative 42 times 10 to the negative 6 coulombs. And then we can use dimensional analysis to figure out how many electrons that is. So one electron, as we saw in the previous problem, has a charge of negative 1.6 times 10 to the minus 19 coulombs. So doing dimensional analysis like this, we can see the coulombs cancels out, and then the unit I'm going to be left with is going to be the electron. I'm going to put this in the chat because it's kind of hard to do. Scientific notation. Okay, and it's a lot. Of course it's a lot. Because electrons are super tiny. It's an interesting calculation. Have you approximate how many electrons are in your body right now? Yeah. Okay, just good old dimensional analysis. Okay. Okay, I'm going to hop over problem 10. I don't know why I included that. It says calculate the gravitational force and the electric force, but that's just kind of tedious.
For this,
Yeah, go ahead.
for question 8, it asks how many excess electrons does she get and by how much does her mass increase?
Oh, yeah.
The mass.
Yeah. So times, and let's see, 9.1 times 10 to the negative 31 kilograms per electron. Is that right? Yeah. I think that's the mass of an electron. All this useless numbers floating around in my head. I thought that, knowing all this stuff would come in handy with trivia, but nobody ever asked questions like this. What's the charge on an electron? It never comes up. Yeah. So if you multiply this out, the answer is approximately 0. It's approximately the odds of you winning the lottery. So it's 2.4 times 10 to the minus 16.
Okay.
The odds of winning the lottery are about the same whether you play or not. Okay, so number 12. Now we'll try and see what happens when we have multiple charges. So these are forces, and if you remember from physics 1, forces, yeah, that's where stuff got interesting. Because they're vectors, and that means direction counts. So I'm going to do a little color coding here, and we're going to put up 3 charges. And the positive ones will be blue, and the negative one will be red. So here we go. So positive 75. That's one charge. And then I've got positive 48. And then I have negative 85. Ooh, this red is popping. Okay. And then the distance between them two, it says 0.35. So these two are going to repel each other. These two are going to attract each other. And then these two attract each other also. So why don't they move? Well, we could certainly think about doing a problem like this where they move, but in physics, what we do is let's handle the simple stuff first, and then we can do the more complicated things later on. So just imagine these are like stickies or something like that, Post-it notes. So there's some kind of minor force just keeping them in place, but we want to find the interaction between the two. Okay, so this is let's start here. Let's do this one first, because the problem says, what's the force on each charge caused by the other two? So let's start off in let's do the force on the plus 75 microcoulomb. So we're going to have 2. We want to start off by figuring out the force by the plus 48 microcoulomb. And then we want to figure out the force by the negative 85. Okay, so we're going to obviously apply Coulomb's law twice. And so this is going to be equal to K times the 75, of course. And just in the interest of space, I'm not going to write out the times 10 to the minus 6. We know that we're going to do that on our calculator. So, and then the 48 microcoulombs divided by 0.35 squared. And see what we get. And then this one is going to be K times 75 microcoulombs times 85 microcoulombs. And this is going to be 0.70 squared. All right, let's go ahead and try this. And we'll see what you get. Now, if your calculator can do a recall of the previous calculation, that is very handy.
Okay. You want us to put answers into the chat box or just say them out loud?
Yeah, no, that's okay. I just wanted to, make sure that got pure interaction in there. Actually, I'm gonna write it down here. So 264. And then I'll write this answer down here. So the nice thing about this is kind of complicated on your calculator, but if you can recall the last calculation you just did, you can go back and then just change the numbers. And that makes that pretty easy. So I'll change 48 to 85. Just hit enter. And then this is 117. And they're newtons. So we should record the total down here. Hopefully you can see that. Just barely. Okay, great. Now you probably have a question about this, which is, well, first of all, let's check the numbers. Feel good about it? Awesome. Now, you should be thinking, how come I didn't put a negative 85 in there? And one of the issues, there was a slide that I said I don't like the way the textbook does it, because it does something like the force of 1 on 2 is equal to the opposite of the force on 2 by 1, and it's really confusing. So what I'd like to do is just reason things out logically. I know that these two repel each other, and we can calculate this. They repel each other with this much force, which is a lot. Right? So that's like, I don't know, 40 pounds probably. And so there's a lot of force between these two trying to push them apart. But the direction of the force on this one is that way, to the left, and the force on this one is to the right. So we really have to logically spell that out. So like I said, this is a force to the left. But the force between these two is attractive. And so this one gets pulled this way, and this one gets pulled that way. Equal and opposite forces, Newton's third law. So the force on this positive 75 gets pulled this way. And so that's a force to the right. So that means that when we do calculating forces, we need to keep direction in mind because force is a vector. So this is a tug of war between two forces, and the force to the left wins. So we're not going to add these together. We're going to subtract them. Okay, so I get 175 left. So the takeaway from this is to not use the plus and minus signs on the charges to tell you which direction things go, because this number, charge, is not a vector. So we use pluses and minuses when we look at motion left and right and up and down for vectors, just to help us keep orientation straight. But this minus sign is not, so it's not mean points to the left, because charges don't point. So this is a scalar quantity. These forces are vectors. So we should reason out what direction they're in.
Wait, so how did you get 175? 264 minus 117 is 147.
Did I make a mistake? Did you do? Yeah. Okay, thank you. Good call. Oh, yeah, now I get it.
Yeah, the batteries must have been loose. Gotta knock them back in there. That's a good
It's
idea.
cosmic rays coming in and
Yeah.
affecting the calculations. Yes. All right, great. All right, so really, if we're going to finish this problem all the way through, we would do 2 more calculations. But let's just do 1 more, just to make sure you're doing okay with this. And let's see where we're at. Yeah, perfect. Okay, so force on. It's my iPad telling me to do yoga. So force on the negative 85 microcoulomb charge. Right. So here we go. So we're going to do by the plus 48 microcoulomb charge, and then the force by the 75 microcoulomb charge. Oh, but you know what? We already did that, because it's going to be the same number that we did here. So this is going to be equal to 117. But now Newton's third law says it's in the other direction, so that's going to be left. And the two attract each other, and so this is going to get pulled that way, so that force is to the left. 117 to the left. And then here, well, we already have made the point that we're going to not factor in the minus sign here. So I'm just going to pull up the previous answer I did and go back in and change things. So the force between these two is going to have a distance of 0.35. And then I'm going to change this to 48.
So it's 48 times 85.
Yes. So 48 and 85 in the numerator and 0.35 in the denominator. And I get about 300. Okay, you smarties out there. Is that to the right or to the left?
To the right?
So these two attract each other. Oh no, he didn't say yes right away.
So 80, wait, what? 85 should move to the left. 48 is moving to the right because they're coming at each other.
They're attracted, right? It's an attractive force. Or you can flip a coin.
So sorry, 48 to the right, 85 goes to the left, right?
Yeah, this one feels a pull to the left, this one feels a pull to the right. So this is to the left. And now when we're looking at the total force, we're not going to subtract them because they're in the same direction. So we're going to add them.
And sorry, for the, when you actually did out the equation, K
Yeah.
48 mu C times 85 mu C over, what did you divide it by?
The distance between these two, which is 0.35 squared. Just like
0.35.
that.
Okay.
All right, great. So just one more. And this is a doozy. This actually is a really interesting situation because it begins to introduce the concept of a field. A field is a very abstract concept, but powerful still. So just because it's abstract, we're not going to run away from it. So in this situation, we have two charges that one plus, one minus. So positive 4.75 microcoulomb charge. So plus 4.75 microcoulombs. Then we have a negative charge of 3.55. Kind of like a washing machine. And then 18.5 centimeters apart. To their centers. So the question is, where is F equal to 0? Assume random charge. So what that means is that we come in here with a sort of like random charge. So look, blue. So that could be a positive charge. Let's say it's positive, right? Now, if I put the positive charge here somewhere, then it's going to be repelled by this charge, so it'll have a force down this way. And it's going to be attracted by a force up here. So that's going to be a force up here. And so since those forces are at different angles, they're never going to cancel out. So this entire region is a no. We're looking for a place where the forces might cancel. Like for instance, can you imagine that there's a point between the Earth and the moon, right? So Earth, moon, and there's a point in between where a spacecraft would feel an equal pull of gravity between the two, right? Can you imagine that? Sounds logical. And it exists. It's called the Lagrangian point. In this region, but of course, that position would have to be on a direct line in between the two. So what we're going to do is define an axis. And recognize that the forces are going to have to line up. So that's why this position where the force is equal to 0 is going to have to be somewhere along this axis. And now we can logically try and reason this out by assuming we have a region 1 and a region 2 that's in between them, and a region 3 that's out here. So where do we start looking for this? What makes sense? Now, if I put my positive charge right here in the middle, then it's going to be repelled by the blue one, and it's going to be attracted by the red one. And both of those forces are to the right. So this is no good. So region 2 is out. No point looking there. Now what about here? If I put my blue square up here, it's going to be repelled by the blue. So that's going to be I don't know if this is helping right here. Let me just try this without this supplemental light. That's pretty dark, isn't it?
Yeah.
All right. We'll go back. I think I'm going to get another one of these lights. Just balance it out. So, once again, if I put this positive charge out here, it's going to be repelled. That's a force to the left. It's going to be attracted by this one. That's a force to the right. So this might work, except the problem is I would always be closer to the bigger charge. And the only way the forces are going to balance is if somehow the distance can be a mitigating factor. So that the pull of the smaller charge could be stronger because we're closer to it. But if we're over here, we're always going to be farther from the smaller charge. So the result of our argument is that region 3 is the place to look. And so what we're going to do is we're going to put a big old X out here. So X marks the spot. That's where we're going to look. And the distance from this point X to here is what we're looking for. But we also need to keep in mind this distance. So we can actually set these two forces equal to each other. So I'm going to have this force over here. So this is going to be K. And it says random test charge. So I'm just going to say Q. And then 3.55. Divided by X squared. And then we'll do the force on the other side. So I'm leaving the microcoulombs there, and I don't know what this is, so we'll just use a variable. And X is what we're trying to solve for. So over here, I'm going to have K, and again, random charge Q, and then 4.75 microcoulombs divided by, and then what do I put in the denominator over there? So I need to keep in mind that it's going to be X, but plus this distance. So this denominator is actually X plus 18.5 centimeters. I'm not going to write the units in there, but and then that's squared. Okay, so it's a tug of war, and we're trying to find a place where the forces are going to balance. And there's a couple of mistakes I made, like, wait, this 18.5, shouldn't it be in meters? Yeah, and then why didn't he write 10 to the minus 6 here? What's that all about? And the reason is that, you know, when I'm doing algebra and I see lots of cancellation possible, the physicist in me really loves that. Because that means, you know, physicists have a tendency to really like when things suddenly become really simple to understand. And contrary to popular belief. So, so when we see an algebra problem where a bunch of stuff is going to start to cancel, love that. So I call it a cancellation fiesta. We're going to have a cancellation fiesta right now. How exciting. All right. All cancellation fiestas use red markers. So K, you're gone. Goodbye, K, you complicating factor, you. Goodbye, Q. Oh, whoa, wait a minute. Pause, rewind. What? This cancels? This random charge doesn't matter? Yes. Because what it turns out is that the interaction of these two charges create possibilities all around them. But this particular place is a place where no matter what charge we put there, it's going to feel zero force. So this is the concept of a field, that each of these positions in space has a particular value that you can use to figure out what the force is if you threw a charge in there. So it's actually sort of like, you know, the old, if a tree falls in the forest, but there's nobody there to hear it, did it fall at all? Well, of course the tree fell down. And in this case, even though we don't have a charge to test it, this is a place where the interaction between these two actually cancel. And we would say the electric field here is zero. And all the other places, all the other positions are all going to have unique values so that if you put a charge there, that field is going to affect the charge. All right, well, a little more on fields on Monday, but all right, so what else cancels? The microcoulombs are gone too. Awesome. And now how do you solve this? Well, we're going to do a little bit of cross multiplication, right? Multiply both sides by x squared, bring this over here, and use the distributive property. Multiply everything out. And once I write that out, I'm still trying to solve for x. So I have 4.75 x squared is equal to 3.55 times x plus 18.5 squared. So it's pretty clear we just bought a ticket to quadratic formula town. And but there's hope. So I'm just going to do one trick just to kind of simplify this for you before we move forward. And in order to do that, what I would recommend doing is that we're going to have to multiply this out. So it would be great if I could get rid of this. So just divide both sides by 3.55 before we get going. And that's going to help out quite a bit. So we'll just do one more line and we'll get it into proper quadratic formula phrasing. Okay, so I'm just going to do 4.75 divided by 3.55 just to make that a little bit easier. So this is 1.34 x squared. And now with this gone, this is a little bit easier to multiply out. So that's going to be x squared. And then plus 2 times this, so 18.5 is going to be 37. So it turns out that the units didn't really matter because there was so much cancellation, and my answer is going to be in centimeters. And that's times x plus, and now I have to square this. So that's 342. Now we should rearrange this so it's in correct quadratic formula orientation. And so that means we're going to subtract each one of these terms from the other side. So this is going to be 0.34 x squared minus 37 x minus 342 equals 0. Solid quadratic formula. All right, I'm going to then take a look at a browser for a second. And so I'm going to head out of this, and I'm going to share my screen. And then we're almost done here. So I'm going to pull up an empty browser. And we're in the 21st century, which has got a lot of perks. COVID-19 is not one of them. And I'm going to here look for a quadratic formula calculator. Nice. Okay, and let's see. The one I like is, I like math, it's fun. Okay, awesome. So now all we have to do is type in the coefficients. So our quadratic coefficient is 0.34. And minus 37. And negative 342. Good, and I got roots. So it says 117 and negative 8.6. I'm over at the whiteboard. Okay, and I'm going to stop sharing and then go back to whiteboard and just finish this off. Because there are a couple of things I would like you to think about. So first of all, the distance between these two is about 20 centimeters, and this is 120. So this axe is actually 6 times further away. It's pretty far out. Why is that? Well, it's because these two numbers are pretty close. So you actually have to go pretty far away in order to make a difference. You know, if this was like 10 and this was 2, then it would be a lot closer. So that's one thing to point out. And then the other thing to point out is that the quadratic gave us 2 answers, right? So what's the minus sign all about? Sometimes we say, oh, forget about that. It doesn't have any meaning. We're just interested in the positive answer. But it actually does have a meaning, which is interesting, and I want you to think about this. Let's think about 8.6 compared to 18. So it's kind of in the middle, but actually a little bit towards this, right around here. So I'm just going to put a little X in here. This position in the minus direction is going to be kind of in the middle, but closer to the smaller charge. So if we did the same problem and both of these had the same charge, this was positive, then region 2 works. So if we said if they're both positive charges and you had to find the place where the force is 0, region 2 is the place to look, and your answer would be 8.6. So if you arrange the quadratic and you do all this work, you'd have a negative 117 and a positive 8.6 for the quadratic. So it actually does have a meaning. And so that's another important thing to keep in mind if you see a situation like this on your quiz for chapter 16, is that if they're opposite charges, then the place you're going to look is outside the 2 charges, but closer to the smaller one. But if they have the same charges, both positive or both negative, then you're going to look in the region in between. And that's the final conclusion for the night. So this gives you enough information to do some problems. And you have enough knowledge to be dangerous. Okay, how did that go? Sound good?
Yeah, sounds good.
All right, excellent. All right. Well, I think we're all done. I'm going to stop recording, then I'll post this up to YouTube. So if you ever want to go back and say, how did we do that again? And now you have enough to do some practice problems with.
And then so for Monday, we've got practice problems for chapter 16 due.
Yeah, correct. Yeah.
And the quiz on Saturday. Okay, for chapter.
Yep. And I'll enter some grades in this weekend, so you can get caught up about that.
Awesome.
And that's the plan.
So, I'm sorry. We just turned in